In this given example, we are to solve the values of x, y, and z given in circle G. Here, we have this situation, EA, or segment EA, or you could also read it as segment AE, and EM, or ME, are both tangent segments to circle G at A and M, respectively. We are going to solve the values of x, y, and z that will be involving all the significant relationships here. So first, let us try to consider what are these notations. X here refers to the angle formed by the tangent segment AE or EA and the radius GA or AG. Next, Y refers to the length or the measurement of segment EA or AE. And finally, Z corresponds to a segment drawn by connecting the center of the circle G towards the point E that is located outside circle G. In solving for the values for the unknown measurements, we need to understand special relationships from a tangent segment and the radius. I'm talking about first the measurement of angle X. Angle X is this angle formed here again by the tangent segment EA or AE and the radius GA or AG. We are sure that this is a radius since this segment started from, or one of the endpoints of this segment is the center of the circle. There is a unique relationship between the angle formed by a tangent segment and a radius, and this is actually guided by a theorem, the tangent chord theorem, or in this case it's just half of the chord, but the point here is when a tangent segment and a radius or a diameter in terms of a chord intersects at the point of tangency, the measurement of the angle formed is automatically 90 degrees. Again, automatically 90 degrees. That would mean this is a 90-degree angle. That's the measurement of angle X. Conversely, looking into at the bottom, we know that ME or EM is also a tangent segment, and GM or MG is also a radius. So the angle formed here is automatically 90 degrees. Or it's right angle. Now, X is already done, but Y and Z are no longer angles. They are measurements. Measurements of segments. In solving Y, which is actually the length of EA and AE, we need to look into closely the triangle formed here. This triangle, the tangent segment, the radius, and this segment connecting the center of the circle G towards the same exterior point where the tangent is occupied. Okay? So this is now a triangle. That's also a triangle. Since it's a right triangle, there is a unique relationship as to the measurements of the legs of the triangle. We could use that later on for Z. But for Y, specifically, I would like you to consider the measurement of EM here. Now, segment EM and segment EA are both tangent segments from the same exterior point, but of course on different points of tangency. There is a theorem that tells us that if two tangent segments are drawn from the same exterior point, of course, the tangent on the same circle, the tangent segments are congruent. This would mean Y as the measurement of AE is just equal to the measurement of ME. That is one of the theorems pertaining on tangent segments here. So since both tangent segments originated from the same exterior point, the measurement of y, which is AE, is also equal to the measurement of ME, which is 15. In short, y is just simply 15 units. That's the value of y. Now, going forward to z, this is where I have shared earlier the presence of a right triangle here. We could use the upper right triangle or the bottom. Nevertheless, they are both right triangle, right? And they have the same measurements here for tangent segments. And could also be here. If this is W, let's say AG is W, AG is equal to 8. Why? Because AG is a radius of circle G. Similar to MG or GM, they are both radii of the same circle. And another statement or theorem in geometry tells us that radii, or radius in plural, of the same circle are congruent. So this is 8, that's also 8. But this is not what we are looking for. We're looking for Z. I would like you to observe this triangle here. Triangle EGM or MEG or MGE. This is a right triangle. The right triangle where the right angle is here, and these are measurements. Since Z is the side directly opposite the right angle, this is what we consider as the hypotenuse of the right triangle. And we know that there is a unique relationship between the hypotenuse and the legs of a right triangle. It tells us that the square of the hypotenuse is equal to the square of the measurements of its legs. This is given to us by the Pythagorean Theorem. Pythagorean Theorem only works for right triangle, and hence we need to understand as well the presence of the hypotenuse. In this case, it is Z. So if we're going to compute this, we will have here 64 for 8 squared plus 225 for our 15 squared. Okay? This is still Z squared, not yet Z, but we're looking for the measurement of Z. In order for us to finish this, we can just take the square root's property or take the root of both sides. We will get the value of Z, which is equal to the square root of 64 plus 225, which is given to be 289. Don't forget that when you take the root of a number, we always consider plus minus. So the value of Z is equal to plus minus. We are just so lucky that 289 is a perfect square of 17. Hence, Z is positive negative 17. But of course, we need to trim it down to our final answer. Since we're talking about measurement and we don't allow negative measurement, Z is simply 17 units, or positive 17 units. So this is the result, or these are the answers for X, Y, and Z, where X is an angle and Y and Z are both measurements of segments. In this case, measurements of the sides of the triangles formed.